Hey, great time. So in today's lesson 4 of Unit 6, we're going to go over transformations of sinusoidal functions. And for the ones watching this video, you'll notice that I had a note template that goes along with this. So I highly recommend that you also look at that as well. So what we're going to cover today is just looking at the roles of the parameters D and C specifically first, and then we're looking at the roles of the parameters A and K, and then of course we're going to look at the parameter of all three A, K, D, and C in the transformation of sinusoidal functions, cosine and sine function, okay? So that's basically the goal for today. So right before I get to that, as I mentioned already, I do want you to open up, if you have it, and again, I know some of you may not have a printer. If you don't have access to print it, that's okay. But if you are able to print it out, I would recommend printing out the transformation of sinusoidal functions, the note template here, because you can use this to, oops, so I'm going to turn off the volume. I just realized that. You can use this to just simply copy down the main points of the note. And probably most importantly, probably most useful for most of you here is the grids that are given to you for you to do the graphs. So just keep in mind, unfortunately, I didn't have a lot of space to do the table values plus do the graphs right underneath it because then everything was cut off. So what I did is I put the graphs kind of near the bottom there. So you have to kind of go further down in the handout. I think it's on page 3 that you'll see all the graphs, page 3 and page 4, and that's where you can do the graphs there. Okay, going back to this, again, totally optional, just letting you know you don't have to do the note template. You could just follow along with the video here and you would be able to figure out most of it, but I'll go through it in any case. So what we are looking at is transformations, which if you recap, we have done transformations actually a couple times now. We looked at transformations of quadratic functions, square root functions, absolute functions, reciprocal functions, although we didn't talk about it as much, and exponential functions. So you can pretty much take a guess. What do you think we can do with sinusoidal functions? We can transform them. So for example, and I just gave this as a small little visual example, both of these parabolas are really just transformations of the original parabola, which is, actually that's a bad graph there. Let me redo that one. So the original parabola, remember, is y is equal to x squared is 0, 0, 1, 1, 2, and 4. And for some reason it got erased there. Let me redo that. Negative 1, 1, and negative 2, and sorry, negative 2 and 4. So roughly speaking, the original parabola looks like this, the parent function, right? And that parent function then got transformed into this one over here and this one over here. We can see here that this one is just basically been translated 3 units to the left. This one's been translated 3 units to the right. This one has gone 4 units down, and this also went 4 units down. They're both opening up. There does seem to be, actually, no, I don't think there's any vertical stretch or compression. It kind of just seemed that way. But again, going back to transformations, if you recall, we simply stretch it by if the A value is greater than 1, and we say that we compress it if it's between -1 and +1. And of course, if it's if it's less than -1, then it's also going to be vertically stretched. Okay. We say it's horizontally compressed by a factor of 1 over k if k is greater than 1, and if k is less than -1. And again, we always say that it's horizontally compressed by a factor of 1 over k, the absolute value of k. And again, that's really important that you remember, because if the k value is negative, it doesn't matter. Whenever we talk about the factor that it's horizontally compressed or stretched horizontally by, we always look at the absolute value of k. So just keep in mind that this is always the one that tends to throw people off. It's horizontally compressed or stretched by a factor of 1 over k. So again, it's horizontally compressed if k is greater than 1, and if k is less than -1. And of course, if it's between -1 and +1, it's horizontally stretched. Okay. And again, I know you went over transformations, so I'm not going to go over it in as much detail. We know that there's a reflection on the x-axis when a is less than -1, and a reflection on the y-axis when k is less than when a is less than 0. That's what I meant to say. And a reflection on the y-axis when k is less than 0. And of course, we translate to the right if d is positive, and translate to the left if d is negative. And again, just be careful with this. It looks like it's positive, right? So for example, if I have something like x minus 4 squared, again, it looks like I'm moving to the left, but I'm actually moving to the right because the d value here is 4. But if I have something like this, x plus 4, and then that's squared, that means that the d value is actually -4, which means we move to the left. okay? So just be careful with that. I think we talked about that before, that the D value, it always looks different in the equation. So just be mindful of that. Again, I would recommend just keeping a list of all these transformations because we're going to talk about them. They basically, the same transformations we looked at before are going to apply with sinusoidal functions. And we'll look at how we actually do that. And of course, the last one, to see if it's positive, it moves up. If it's negative, it moves down. So let's just get straight to it. How do we transform these sinusoidal functions? So in all these examples, I'm going to look at transforming the sine function, but keep in mind that all these transformations would work the exact same way for a cosine function. So I'm going to focus my attention on the sine function just because that's easier, but really, it's not really easier. It's just the first one there. But really, we could have transformed the cosine function. It would have been the exact same way. Okay, so for the first one, let's look at what the effect is for the D parameter right here, D value. So what happens if I change the D parameter there? So what I'm going to ask you to do is graph out f at x is equal to sine x, f at x is equal to sine x minus 30 degrees, and f at x is equal to sine x plus 60 degrees. And then what do you notice? So I'm going to go back here, and this is the point where I'm going to ask you to, I'm going to ask you to go to the note template that's on the day-by-day outline. So if you go on note template here, I'm going to be asking you to fill in this table values. Again, when you're filling in the table values, my suggestion is simply, you can use a calculator for this. I know for the first lesson 2, we actually didn't use a calculator, but in this case, I do want you to use it just because it will take quite a while if you're actually not using it. And I think it's just going to take longer. So just to make life a little bit easier, let's speed up the process. Let's use a calculator, okay? So I want just to figure out what the values for each of these functions. So for sine x, obviously, I'm hoping you know this by memory. This is going to be 0. We know that this is 1/2 or 0.5. Actually, I'm just going to write it as a decimal. I think we saw this last time, 0.5, 0.71. This is 0.87. Again, this is just an approximation. Oops, and I did something wrong, sorry. I'm going back to the ones I did before. Oops, I forgot that it's not 45 degrees, it's 60 degrees, 0.87. Approximately, that's 90. And then we go back to 0.87, 0.5, and this is going to be 0, and then we go negative 0.5. I'll let you kind of finish the rest of it. So again, grab a calculator and figure out what the sine, oops, I don't know what happened there. Figure out what the sine of each of those x values are. And for the second graph underneath, the second table of values underneath, we're going to follow the same steps, except it's going to be x minus 30. So we're simply going to take 0 minus 30, right, for the first one, and then we take the sine of that. So what is the sine of negative 30? The sine of negative 30 is 0.5. So negative 0.5, sorry. So I'm just going to write over here, negative 0.5. Now we follow the exact same step. We're going to take 30 minus 30. So we take 30 and we simply sub it into this function here. So again, for this one right here, I hope everyone's kind of clear on this. What I'm doing is I'm taking the x value and I'm substituting it into this function here. So obviously 0 minus 30 was negative 30. And then I take 30 minus 30, that's sine of 0. And I know the sine of 0, I can use a calculator for it, but I think everyone knows it's going to be 0. For the next one, I take 60 minus 30. And again, 60 minus 30 is going to be 30 degrees. And I know the sine of 30 degrees is actually the answer up here, 0.5. So I think most of you can see what's already happening here. You're going to notice I'm going to start getting the exact same answers as the table at the top, because obviously 90 minus 30 is 60. That means I'm finding the sine of 60, which is already up here. So really, I don't have to do any extra work. I don't even need a calculator. I notice that my answers actually just repeat. So the next one, 120 minus 30 is 90, which we know the sine of 90 is 1. So I just fill in this table, and I'll let you just fill it in on your own. And again, I know that you can figure this out on your own. I think everyone kind of sees a pattern here. We're simply repeating the y values, but we're reaching the same y values, but we're reaching them a little bit later, right? So we can see here that we're reaching the same y values, but it's occurring at we're reaching the same y values, but we're reaching them faster. That's what I meant to say. So you're reaching them at 30 degrees to the right. That's really what's happening here, right? So I can see here that I still get the same y value as sine of 180, but I have it when x is equal to 210. So I think you're already starting to see what's happening here. You get the same y values, just been shifted 30 degrees, right, to the right. And what do you think is going to happen? We have sine of 60x plus 60. Well, let's just do the same math here. Sine of 0 plus 60. So 0 plus 60 is 60 degrees. And then, of course, the sine of 60 degrees, we already know what the answer is. It's up here in the first table, 0.87. Sine of 30 plus 60, 30 plus 60 is 90, and the sine of 90 is 1. And I think everyone can kind of see what's going to happen here. I'll let you fill in the rest of the table, but essentially the only difference is that you're taking that x value and you're adding 60 to it. So again, I think you're starting to see what's going to happen here. We're going to reach the same y values, but we'll reach some 60 degrees later than we would have in the original sine function. So what is the effect that this has? Well, let's look at the effect of the d value. So what we notice is that if our original function is sine x in red, and our transformation sine of x minus 30 degrees, well, the x minus 30 degrees, what it really does is it shifts our graph 30 degrees to the right. And that kind of makes sense with what we learned about transformations, right? We know the d value simply moves it to the left or to the right. So it makes sense that all it's doing here is simply moving our graph to the right 30 degrees. And that's all it is. And of course, what does sine x plus 60 degrees do? Well, it does the opposite. It basically takes our graph and it shifts the original graph. And again, all these changes happen to the parent function here, sine x, takes that original graph there and simply moves it 60 degrees to the left. So all the key points here will get moved 60 degrees. Actually, all the points in the graph, but really we focus on the key points here, all get moved 60 degrees to the left. So as an example, just so we see points more clearly here, just kind of highlighting the points where they moved. In the original function 0, 0, that point now gets moved to negative 60 and 0. The point 90 degrees and 1 now gets moved to 30 degrees and 1. So same y value, just the x value that changed, right? It's 60 degrees to the left. 180 degrees and 0 now gets moved to 120 degrees and 0. 270 degrees and negative 1 now gets moved to 210 degrees and negative 1. And 360 degrees and 0 now gets moved to 300 degrees and 0, right? So we can see here that all the points have simply been shifted 60 degrees to the left, okay? Does that make sense so far? Hopefully it does. So again, very similar transformations to what we saw before, not too different. And I'm hoping that kind of makes sense, right? So essentially the fact that D has already, what we're starting to notice is that it simply makes our graph get shifted either to the left or to the right. And it gets shifted to the right if D is positive, it gets shifted to the left if D is negative, which is exactly what we expected, right? So the good thing is there's no surprise there. We knew that was going to happen. Also, you're probably wondering how do they actually get these graphs to work? If you want to see what they look like on Desmos, you're more than welcome to do that. Again, I mentioned this already, Desmos is a tool. It's not going to be the answer, but you can certainly use this. Now, one thing I want to mention when you're graphing with Desmos, this is really important when for the culminating project, if you decide to do the Desmos project there, you're going to have to change your scale in order to see the graph more clearly. My suggestion is switch it into degrees first. It'll make a lot more sense. Now, when you do that, the graph looks a little bit bizarre. Now, what you're going to want to do, because you're going by degrees, again, you want to change your x-axis, what it's the scale for the x-axis. So in our case, we want it to go from negative 360 degrees to maybe, I always like to go a little more than 360 degrees. Let's say 500 degrees, right? So what the x-axis will do is the scale for the x-axis will tell us how far we go in degrees, right? So negative 360 degrees to positive 500 gives us a good range there. And for the y, let's say we'll go by negative 10 to maybe positive 10. And it depends on the problem, right? We might want to go lower. Maybe we want to see the graph a little more clearly. We can go negative 5 to positive 5. Or if you want to see even more clear than that, you can do negative 2 to positive 2, right? Again, you can kind of play around with this a little bit, but I think the main one to change is the x-axis there. So I'm going to do negative 5 to positive 5. And you can always change that later on. And then I'll say we'll go by ones. And over here, for the degrees, I personally like to go by 30. I feel like it's easier to see there. And you can also change it so you can see it more clearly there. And if I zoom in, this is a bit of an easier graph to read compared to what I had before. So if I compare this graph with sine of, what was this? Sine of x minus 30, we can see here that's just been shifted 30 degrees to the right. And then if I have sine of x plus 60, oops, there you go. It's just been shifted 60 degrees to the left. Does that make sense so far? Okay, so I'm going to go back to the PowerPoint here. Again, when you're filling this out on your own, You don't have to follow no template, but if you're wondering how you fill it out, you simply fill out the table, and then you're going to go to the very bottom here, which says the graphs. I apologize that I had to kind of split it up. It's just for space there. You plot the 3 graphs together on the same grid. I don't want you to do them separately. I want you to do them on the same grid, just so you can actually see the effect of the transformation. So I'm going to go up to the next example. So looking at the C parameter. So what is the change that we're going to have when we change the C parameter? So when we change the C parameter, which means that we add a constant at the very end of the equation, what happens to this graph? So let's take a look. So what I want you to do is graph sine x plus 2, and graph sine x minus 1. And then I'm just going to ask you, what do you notice? Pretty simple. All these questions are very similar, right? So for this next one here, I want you to go to your table and just tell me what you notice here. So I'm going to fill in the first one. And again, I'm going to do this really quickly because we already did it. 0.87. 7, just to give you an idea here. Okay, I'm too lazy to do the rest of it. I think you can do the rest on your own. So what I'm going to ask you to do is figure out what the sine of x plus 2, sine x plus 2 is first. So because we have sine x plus 2, then I simply take sine of 0 plus 2. So I'm taking my x value and then I'm adding 2. Sorry, I'm taking my x value, subbing it into the function. So I take the sine of the x value and then I add 2. So sine of 0 plus 2 is going to be 2. Sine of 30 degrees plus 2 is going to be 2.5. So all I'm doing here is I'm simply adding 2 to our previous answer. So I take the previous y value and I simply add 2. So sine of 60 degrees plus 2 is 0.87 plus 2, which is 2.87. And of course, the sine of 90 degrees is 1, but I add 2, that gives me 3. And then I continue this on. And I think everyone can see what's happening, right? You don't even have to do any math here because you can see here that my y values are just repeating. So this is going to give me 2.5 and 2 and so on. But I think everyone kind of sees the effect there. So what do you think happens with that C value? If I add it, I'm bringing all the points up, right? So what's happening with my y values? My y values are just increasing by 2, which means my graph just vertically shifts up. And what do you think is going to happen if I subtract the 1, for example? Then I simply take the sine of 0, sine of 30 degrees, sine of 60 degrees, whatever it might be, and I simply subtract 1. That means I have -1 for the first one, because I take sine of 0 degrees, which is 0. I subtract 1, I get -1. I take sine of 30 degrees, which is 0.5, and I subtract 1, that gives me -0.5. I take the sine of 60 degrees, which is 0.87, and I subtract 1, that gives me negative 0.13 there. Then the next one, and sine of 90 degrees is 1, and then I subtract 1, it gives me 0. And I think you kind of see what's going to happen here. The y values start repeating. There we go. It doesn't always work this way. It's just because obviously it's a simpler example here. But you can kind of see here that there's obviously going to be symmetry with these x values. And we continue this on, and I'll let you finish the rest of the table there on your own. So what we end up seeing is, going back to our graph, we end up noticing that really that C value, all it does is either shifts the graph up if the C value is positive. So in this case, because it was sine x plus 2, we just simply take our previous y values and add 2 to them. That's all we did. We're simply adding 2 each time. And of course, if the C is negative, we can see here that we are just taking our previous y values from the original sine function, and we're just taking away 1. So we take away 1 from each of the y values in the original sine function. And that's all we're doing. Hopefully that kind of makes sense so far. So again, that's what the transformation, that's what happens when we change the parameter C. And again, I hope that one kind of makes sense. It's really similar to what we saw with parabolas and square root functions. I personally think the C parameter is probably the easiest one to understand. Basically, if it's positive, you shift it up. If it's negative, you shift the y values down, right? So not too tricky there. Let's look at what happens with the A parameter. So again, for this one, we're going to graph sine x, sine of 2x, the 2 times sine x, and then -1/2 sine x. So let's see what the graphs of these functions look like. So let's take a look by doing our table values. So we know how to do our table values here. Again, let's go back to the example at the bottom. Oh, by the way, I forgot, for the last example we did, you simply draw the graph over here. So you have the space here to draw the graph of the transformations when I change the C value, okay? So let's go back up and let's do the A parameter. So for this one, we're going to figure out what happens when we change our a value. And I think most of you can take a guess what's really happening. The transformations are pretty much identical to what we saw before. The only difference is that instead of applying these transformations to, a square root function, a parabola, we're just applying it to a sinusoidal function. So in our next one here, we just fill it in 0.5, 0.87, 1, 0.87. I think you know what to do now. 0, and I'm not, like I said, I get lazy with this. I'll let you just finish that on your own. Again, if you're wondering like how I'm getting these values, I'm just subbing them into the calculator, right? Or you just know them by memory, especially some of the key points here, like this one right here, 90 and 1, 90 degrees and 1, 180, 180 degrees and 0. You should know those by memory. And same with 270 degrees, that would be -1, and 360 degrees, that's going to be 0. So what we're going to do here is we're simply going to find out what the y value is for the function 2 sine x. So that means, and again, the order doesn't matter. I'm going to find the sine of the angle, and then I'm going to multiply it by 2. So be really careful with the order you're doing it in. So in this example, I'm taking the sine of each of these angles here. So 0 degrees, 30 degrees. By the way, I forgot the degree symbol there. I think I just kind of, fortunately, I rushed a little bit with this one. I was trying to get the equation on there. With the equation, for some reason, the space in the table was really, really limited. So I decided not to put degrees, but technically there should be a degrees there, okay? So when we take the sine of 0 degrees and then multiply by 2, what do we get? Well, the sine of 0 degrees is 0, and then we multiply by 2, we get 0. The sine of 30 degrees is 0.5, and then we multiply by 2, and then we get 1. The sine of 0.60 degrees is 0.87. We multiply by 2. What does that give us? That gives us, so 0.87 multiplied by 2, that gives you 1.74, right? And then the sine of 90 degrees is 1, and then you multiply by 2, that gives you 2, and then you pretty much know what's going to happen here. All the y values start repeating again. The sine of 150 degrees, we already know that's going to be 0.5 times 2, that's going to give you 1, and then this sine of 180 degrees is 0, times 2 is 0, and so on, okay? I'll let you just continue that there, and now we're going to figure out what the sine of, what the y value is for the function -half sine x. So again, we're going to follow the exact same step. We're just going to find the sine of each of these angles here, and then we're going to multiply by -1/2. So the sine of 0 degrees is 0. You multiply by -1/2, you get 0. The sine of 30 degrees is 0.5. You multiply by -1/2, you're going to get -0.25. And again, it's going to be negative because it's a negative a value. So the sign switches, right? So then we have 0.87. We multiply by -0.5. That gives you, so what's half of -0.87? That's going to give us -0.4325. Sorry, 435. Sorry, a mistake there. And then the sine of 90 degrees is 1, but then we multiply that by -0.5. Sorry, -0.5, because we're multiplying there. And that ends up giving us -0.5. And of course, we start noticing that all our y values are going to repeat. I'm not going to finish the rest of the table there for you, but again, you can do it on your own. Simply take each of these x values and sub them into this function here, and you should be able to fill out the rest of the table on your own. So I'll let you do that. So when you do this, you end up getting these two graphs. And again, do the graph on the handout there. I know you guys can do it on your own. I'll show you what the graphs actually look like. So in red is our original parabola. Sorry, not original parabola, our original sinusoidal function. And we can see here that in green, we have the graph of 2 sine x. So what do we notice? Well, all the y values are simply multiplied by 2. So that means that the graph is vertically stretched by a factor of 2, just like we vertically stretch parabolas by a factor of 2 if the a value was 2, right? Nothing different at all. And of course, what happens when the a value was -1/2? Well, the difference is two things. We reflect it on the x-axis. So we can see here that the x-axis is right there, and we simply reflect it. So instead of opening up and then, instead of going up and then going to the middle, then going down the middle, we go the opposite direction. We start from the middle, the equation of the axis, we go down to the minimum, we go back up to the middle, the equation of the axis of the curve, then up to the top to the maximum point, and then back down to the middle. So we kind of just go in a bit of a different direction, right? So we reflect it on the x-axis. And of course, we can see here that we are vertically compressing it by a factor of -0.5. Sorry, by a factor of 0.5. So again, whatever the a value is, remember, we always take the absolute value whenever we talk about the factor it's vertically stretching or compressing by. So I hope that kind of makes sense so far. Again, very similar to what we did when we looked at transformations of parabolas, square root functions, whatever function we might have. So not too different at all. So again, I think you're starting to kind of see what's happening here. The A value is really having this exact same effect as before. It's either vertically compressing it or vertically stretching it, as well as possibly reflecting, making the graph reflect on the x-axis if A is negative, which is the case in this example here. All right, let's look at the last set of examples here for the transformations. And then once we do this, we're going to summarize all our findings here. So for the graph of a sine of kx, so if I have a k value in front of the x, so notice the difference. In the other example, I had the a value in front of the whole entire function, which means that I had to take the sine of the function first, the sine of the x value first, and then multiply by a. Here, I'm taking the k value and multiplying by the input x, then taking the sine of that. So it's a little bit different, right? It's a different effect there. So in this case, the k value is being multiplied by the x value, and then we take the sine of that. So it's a different order. So what I'm going to ask you to do is simply graph out sine x, sine of 2x, and sine of a half x. And then I'm going to ask you what you notice. Now keep in mind, k could be negative. It is possible for it to be negative, but we tend to not cover this as much. So just a little reminder that it could be negative, but we will tend to focus more on when k is actually positive. If it is negative, it doesn't have as much of an effect. You'll kind of see why. But we also honestly just tend not to focus on it as much. So it's not going to be a big focus in this course. Maybe later on in grade 12, you will focus on it more. But just in this course, I'm trying to focus just more on the ones that you'll see the most. So I'm going to go back to the table values here. And I apologize, guys. I know it's a little bit tedious to do table values. I apologize, but it is a good way to kind of get adapted to looking at what the graphs look like. Again, very, very tedious. I know that, but I'm going to fill it in really quickly and I'll go fast with this, as fast as I can. Okay, and this is going to be 0. Okay, so what we're doing in this case is we're simply going to take our x values, we're going to multiply it by 2, and then take the sine of that. So notice that the order we do it in is different. So we are taking the product, we're going to find the product of 2 and x first, and then take the sine of that. That's different than the other example. In the other example, we took the sine of x, of the angle, and then multiplied by 2. It's a little different, right? In this case, we're taking the finding the product and then taking the sine of that. So we're going to take 2 times 0, which is 0, and then take the sine of 0, which is 0. Then we're going to take 2 times 30 degrees, which is 60 degrees. And then we're simply going to multiply it by, take 2 times 30 degrees, which is 60 degrees. And then we take the sine of that. The sine of 60 degrees is going to be 0.87. And we know that because we can just look at the table above, right up here. Then for the next one, we take 2 times 60 degrees, which is 120 degrees, and the sine of 120 degrees, we know what it is. It's up here, 0.87. And then we take 2 times 90 degrees. 2 times 90 degrees is 180 degrees. Sine of 180 degrees is 0. Okay. So I'm going to let you complete the rest of this table here, but I think you're already starting to see what's happening. If you look at the actual tables back side by side, you might already notice this. You'll start to realize that you actually get the same, the x values in this case, the y values are not any different, right? The y values did not change. It was simply the x values and how they coordinate with each other that changes. So for example, the 30 degrees right here, the sine of 2x, when I have, the y value of sine of 2x when x is equal to 30 here is actually equal to the previous graph, the original graph, when x is equal to 60 degrees. So I reached the same y values before, but I basically reach it in half the time. And again, I think I mentioned this already. I always like to think of k value as representing speed, or how fast or how slow your graph is going. So if I have a k value of 2, what I always think of this as is that I'm moving twice as fast. So if I'm moving twice as fast, think about it this way. I'm reaching the same y values as before, but I'm reaching them in half the time. So that means that I would reach the y value of 0.5 that belong to x is equal to 30, but I'm going to reach it, instead of reaching it at 30 degrees, I'm going to reach it at 15 degrees. I'm going to reach this y value of 0.87, but instead of reaching it at 60 degrees, I'm going to reach it in half the time, which is 30 degrees. So again, if you're moving twice as fast, think about it as running, right? If you're running twice as fast as someone else, that means you're going to reach the same, let's say you're in a race, you're going to reach the same milestones except that you're going to reach them in half the time as the other person because you're moving twice as fast. So that means that I'm reaching, for example, a couple more examples here. I'm reaching the y value of 1, but I'm going to reach it at 45 degrees instead of reaching it at 90 degrees. I'm going to reach this y value of 0.87, but I'm going to reach it in half the time, which is 60 degrees instead of 120 degrees. And of course, I'm going to reach the y value of 0, but instead of reaching it at 180 degrees, I'm going to reach it at 90 degrees. So I think you can kind of see what I mean by that. So really, what is this doing to our graph? So what it means graphically is that this graph is actually going to be more compressed. It's going to be compressed horizontally. So everything's kind of squished in a bit more horizontally there, right? So the y values did not change. It's just the x values that change. Okay, let's take a look at what happens when we have the sine of half x. So for sine of half x, we're simply going to take the x values here and we multiply them by half and then take the sine of that. So what is the sine of 0 times a half? So 0 times a half is 0, and the sine of 0 is 0 degrees is going to be 0. That's pretty boring. So nothing special happens with 0, right? For the most part. Let me just change that. And again, just because that's the sine function here. So this gives me 0. Then for the next one, the sine of a half times 60 degrees. So half of 60 degrees is 30 degrees. So what is the sine of a half? Sorry, what is the sine of 30 degrees? Well, we can clearly see here the sine of 30 degrees would be 0.5, which is the sine of 30 degrees is 0.5, which is the same y value we have here at the top. We've continued this on the sine of 120 degrees. So 120 degrees is, the sine of half of 120 degrees. So half of 120 degrees is 60 degrees. And we know the sine of 60 degrees is 0.87. So notice that we get the exact same y values as the first graph, the sine graph, except that the x values are the only ones that switch, right? So all these x values have changed. So we notice that we reach the same y values as before, but we reach them a lot slower than before, right? So we're reaching them in basically half the time as before, right? So again, what does this mean? That means it's horizontally stretched by a factor of 2, right? It's going to be the reciprocal. And again, I think this always throws people off. Why is it the reciprocal? Again, think about speed. If the k value is a half, that means you're going half as fast as you used to, which basically another way of saying that is you're going twice as slow. So if you're moving slower, that means that you're reaching the same y values, but you're reaching them in twice the time, right? So for example, if I have two people running here, well, it's supposed to be a person. It looks like their head is a little off. Let's see. So these two people are running, right? So yes, they are going to reach the same milestone. Let's assume that they actually finished the race. So 1, 2, and 3. There's 3 milestones. And actually, let's make it an even number 4. Okay. So if this person's running twice as fast, they're going to reach the same milestones, but they're going to reach them in half the time, right? So this person who's faster is going to reach that milestone of 2, but they might reach it in like, I don't know, 15 minutes. But the other person who's twice as slow, or you can think of it as going half the speed, is going to reach that milestone of 2, but they're going to reach it in 30 minutes instead. So I kind of noticed that the y value, which is in this case the milestones, are going to be the same, but the time in this case, that's the x value, is going to be different, right? And we can see here that it would make sense that if you're going at half the speed, then you're going to reach the same y values, but same points, but in half the time. Sorry, but in twice the time, right? Because you're moving slower there. So I hope that kind of makes sense what's happening with the transformations. And I know sometimes transformation is going to be a little bit tricky, but again, I'm hoping this kind of makes sense so far. Again, the graphs of the transformations for the last one here, you can just do it on this final graph there. So again, what does it actually look like? Let me show you here. So we have the sine x, which is the original parent function. We can see here is going from, it has one cycle from 0 to 360 degrees. And that is going to be our original, I keep saying parabola, original function there. And notice that the period here, I always like to notice what the period is for each of these functions, is 360 degrees. So what do we notice when we look at the green function there? Well, in the green function, for sine of 2x, we notice that we reach the same y values, but we reach them in half the time. So if you actually look at the green function there, we can see here that the period is going to be 180 degrees. So notice that the period, which is basically the length of one cycle, so this is one cycle here, up to 180 degrees, that's half of the period of 360 degrees. And again, that kind of makes sense because if you are racing with someone, we talked about this, and you're moving twice as fast, that means you're going to finish the race in half the time. So it makes sense that the period would be shorter. And we noticed that for sine of a half x, we reach the exact same y values, but we reach them in twice the time. So instead of us having a period of 360 degrees, we actually end up getting a period of 720 degrees. That's our new period there. So I hope that kind of makes sense so far. And that's essentially what these three graphs are going to look like. So what's our big conclusion here? So if you have the function sine x, we notice that we're going to have the following, they are going to have the following transformations based on the A, K, D, and C parameters. So we can transform our, actually, I just realized that I wanted the table first. Sorry, I think the order I did this in was a little off, but that's okay. So the transformations are listed on this table here. So we have A, K, D, and C. So what do each of them do? Well, the A value, we talked about this, it stretches it vertically by a factor of the absolute value of A, right? We always take, whenever we talk about the factor, it's the absolute value of A. So if it's negative, you still say, you just ignore the sign, right? So we say it's going to be vertically stretched if A is greater than 1 or if it's less than -1, and it's vertically compressed if A is between -1 and +1. And then we also say that it gets reflected on the x-axis when A is less than 0. For K, we follow the kind of similar, exact same rules as before. It's the transformations have not changed. We say it's horizontally compressed by a factor of 1 over the absolute value of K if K is greater than 1 and if K is less than -1. And of course, it's between -1 and +1. We say it's horizontally stretched. And of course, we say that it's reflects on the y-axis if K is less than 0. This one we don't talk about as much, but just letting you know that that is one of the transformations as well. And then, of course, for D and C, I mean, those are pretty self-explanatory. You move to the left or to the right, depending on whether it's positive or negative. So you move to the right if it's positive, you move to the left if it's negative, you move up if C is positive, you move down if C is negative. Pretty simple. So as I mentioned already, you normally want to apply the transformations by applying them to the 5 key points. You wouldn't want to do this for every single point, 30 degrees, 60 degrees, that would take way too long. Focus on the key points, and then you can have a decent, pretty good graph, I would say, for the transformation there. And as always, I mentioned this already, you always want to apply the vertical and horizontal stretches and compressions before, as well as the reflection on the x or y axis, before you start translating vertically or horizontally. And again, whatever transformations we can apply to the sine function, you can apply it to the cosine function. So this last part here is actually going over the rules the little shortcuts that we use. And we will talk about the shortcuts. And if you remember, Ms. Bao made a handout for you, Unit 1, going over the transformations and kind of the mapping rule that we had. I highly suggest that you go over that handout again. The good thing about that handout is that applies to any function. It's not just these types of functions, right? Exponential functions, sinusoidal functions, square root functions, any type of function you can list, the transformations are exactly the same. So if you understand that really well, then this is actually quite easy. So the general rule here kind of makes sense that for the A value, because it only affects the Y coordinate, then obviously we're only going to be changing the Y coordinate. And what we do is we simply take the Y coordinate and multiply by whatever the A value is. For the K coefficient, or is this the K parameter, we simply multiply the X coordinate. And I'm sorry, I made a typo there. Did not mean multiple. Multiply the X coordinate by 1 over K. And again, notice that we don't put the absolute value of K. That's not a typo there. And the reason for that is because if it's negative, then we also have to consider that sign as well. For the D value, what we do is we simply add the D value to the X coordinate. So if it's positive, again, this is just a little reminder that, if it's X minus D, it looks negative, but it's actually positive. And if it was X plus D, you know that it looks negative. Sorry, it looks positive, but it's actually negative. So you're going to the left. And then, of course, the last transformation is that you can add whatever the C value is. So let's look at an example here. If I asked you to transform this function, -2 times sine of 2x minus 45 degrees plus 1. So how would I do this? So I want to first transform the key points, as I mentioned here. And then, of course, when you're done, I have a couple of follow-up questions. What's the domain? What's the range? What's the amplitude? What's the period? What's the phase shift? And what's the vertical shift, which is the equation of the axis of the curve. So a lot of questions on there, but let's take it step by step. So the first thing you want to do is recall what are the key points of the sine function. So the key points of the sine function, hopefully you know them by memory, is 0 degrees, 0, 90 degrees, 1, 180 degrees, and 0, 270 degrees at -1, 360 degrees, and 0. Or you can remember the graph here. And again, you have access to your graph. And again, your test is open book. So yeah, that advantage. This graph was given to you in lesson 3. So here are all your key points. And I think you can do the rest on your own there. So 270 and -1 and 360 and 0. Perfect. Okay, so what we're going to do is we're going to apply the transformations to each of these points. So starting with 0, 0, what I'm going to do is I'm simply going to apply step by step what the transformation is. So I wanted to do transitions for this. Unfortunately, I can only give you the answer all at once with the table. So that's okay. Let's just go through it step by step. So I'm going to do, whenever I talk about transformations, I always like to go in this exact same order that they appear in the equation. So A, K, D, and C. I like that going in that order. You can switch the order. We can do K before A. That's fine. Or you can do C before D. But you always have to do the horizontal and vertical horizontal and vertical compression and stretches and reflections before you do any translations. Okay, so that's the important thing. So let's apply the A parameter first. So we know that the effect that this is going to have is it's going to take our Y value, and we're going to take our Y value multiplied by A. So what that means is I'm going to take whatever my Y value was in the original parent function 0, 1, 0, -1, and 0, and I'm simply going to multiply each of the Y values by -2. So I take 0 and I multiply by -2, that gives me 0. Then I take 1 and multiply by -2, that gives me -2. Then I take 0 and I multiply by -2, that gives me 0. And I take -1 and I multiply by -2, that gives me +2. And then I take 0 and I multiply by -2, and that gives me 0. So pretty simple so far, right? All I'm doing is taking my Y value and multiplying by -2. So I can see here that these are the new resulting points, okay? So just so you know, in this case, I'm applying the transformation step by step. If any of you are wondering, could you go faster with this, or could you just use the mapping rule? Absolutely, you can use the mapping rule. And if you want to just use the mapping rule, you want to skip this part in the video, you're more than welcome to do that, right? So if any of you are really good with the mapping rules, just apply the mapping rule, okay? I'm just going step by step just to make sure everyone's kind of following how I'm doing this, okay? For the next one here, I'm going to take my previous points, 0, 0, 90 degrees and -2, 180 and 0, and so on. And I'm going to simply apply the K value. So the K value means I have to take whatever the X value is, and I multiply by 1/K, or another way of writing this is X divided by K. It's the same thing, okay? So I can either write it as 1/K times X or X divided by K. So what I'm going to do now is I'm going to take my K values, sorry, my X values, the previous ones, which are these ones right here, and I'm going to divide each of them by 2 or multiply by half. So dividing by 2 or multiplying by half is the exact same thing. So I take the 0 degrees right here, and I'm going to divide by 2 or multiply by half. It really depends how you want to look at it. So I'm going to divide each of the X values by 2. So 0 degrees divided by 2 is 0 degrees. 90 degrees divided by 2 is 45 degrees. 180 degrees divided by 2 is 90 degrees. 270 degrees divided by 2 is 135 degrees. And 360 degrees divided by 2 is 180 degrees. All right, so far so good. Let's look at the next one. So in our next group of points, I'm going to be, sorry, for the next two transformations, I'm going to be looking, let's go in order here. So for D, I have a D value that is 45 degrees, and I go back to my equation here. It's X minus 45. So again, looks negative, it's actually positive. And again, what am I changing in the D? I am, with the D coefficient, sorry, D parameter, I'm changing the X coordinate, right? So I'm changing it by simply adding whatever the D value is. So in this case, I'm adding 45 degrees. So I'm going to add 45 degrees to the X value. So add 45 degrees here. So 0 degrees plus 45 degrees is 45 degrees. 45 degrees plus 45 degrees is 90 degrees. 90 degrees plus 45 degrees is 135 degrees. 135 degrees plus 45 degrees is 180 degrees. And 180 degrees plus 45 degrees is 225 degrees. And this is going to be our new point. So 45 degrees in 0, 90 degrees in -2, 135 degrees in 0, 180 degrees in 2, and 225 degrees in 0. So notice that in the last two steps, the y values have not changed, but the y values still changed from the original transformation that we had, which was A, right? So we're just simply taking the previous values and just changing them step by step, right? And there is a shortcut to this, by the way, and we'll go over the shortcut. And the last transformation. So our last transformation is always the easy one. The C, so what it does is you simply add the C value to the Y coordinate, again, because we are simply moving it up if C is positive, or we're moving it down if C is negative. Pretty simple. So in our case, C is positive, which means that we're going to be adding the C value of 1 to the Y coordinates. So we're going to be changing the Y coordinates. So the previous Y coordinates were 0, -2, 0, 2, and 0. So we're just going to add 1 to each of them. So we add 1 to this Y coordinate, we get +1. We add 1 to -2, we get -1. We add 1 to 0, we get +1. We add 1 to 2, we get 3. And we add, oops, it's supposed to be a 1. And then we add 1 to the Y value of 0, we get 1. And this is our resulting XY pairs there that we have for our graph. So we have 45 degrees and 1, 90 degrees and -1, 135 degrees and 1, and 180 degrees and 3, and 225 degrees and 1. So again, what this graph actually looks like step by step, I plot, and again, this is the way I would do it. I would just plot out the key points. So where did the key points get mapped to? So 45 degrees and -1 is right there. Then we had 90 degrees and -1 is right there. This is 135 degrees and 1, 180 degrees and 3. And then our last point was 225 and 1. And we can see here that this is just coming from the last column in our table of values. And again, you don't actually, we're not given what the rest of the graph looks like because we only transformed the 5 key points, but you can pretty much take a guess what's happening here. And that's why I did the dotted lines there. These points weren't given to us, but I think it's pretty clear how you would find them. You would follow the same pattern as before. You would notice that the Y value is simply going to repeat to the left or to the right. So if we kind of follow 180 degrees, we can see here that every 180 degrees, a cycle will continue on. And again, where am I getting 180 degrees from? The fact that the period is simply going to be half of 360 degrees. So half of what it used to be, right? So we can see here the period is 180 degrees. So every 180 degrees, the cycle keeps repeating it over and over again. So again, I only plotted out what the key points look like, but I think you can kind of continue, you can deduce what's going to happen for the rest of the graph there. So this is actually what the graph looks like when I plot the original one. And again, the original one is, so in green, this is sine x. And this right here is the transform function, which is -2, oops, y is equal to -2 sine of 2x minus 30 degrees, or sorry, minus 60 degrees, I think it was. No, 45 degrees, sorry. Sorry, just writing it down here. +1. So we can see here that was our original function there. Sorry, that was our transform function. So this red graph right there is the graph of the transform function. So we're just looking at them side by side there. So what do we notice? Well, side by side, this is what, and again, this is using technology, what the graph looks like. I wanted to show you a little more accurately what the graph looks like when it's a bit more precise. So we can see here that I've only highlighted one of the cycles there. So if you put this on decimals, you can actually see what the whole entire graph looks like. But I want to focus our attention on this cycle right here, because this cycle is basically shows all the transformation of those 5 key points on the original sine function, right? So when we just look at the first cycle of the sine function, so that cycle from 0 to 360 degrees now got moved to a cycle from 45 degrees to 225 degrees. And again, we can continue the cycle over and over. So what do we notice? So the question asked us for the domain and range. So let's look at the domain. Well, even though we focus just on one cycle from 45 degrees to 225 degrees, because that's where the 5 key points got transformed to, we actually can see very clearly on this graph that this graph goes on forever. And if we actually plot this out, we can actually see that ourselves. So if I go to decimals here, I'm just going to show you what it looks like. So we have sine of, it was -2 2 sine of 2x minus 45 plus 1. So you can see here that this graph actually goes on for a long time, right? It goes on forever there. So there's really no end to it. If I zoom out of this graph, I can see that the x value, there's no limit to it, right? There's no restrictions. There's no point on the x axis where the graph doesn't exist. It just goes on forever horizontally, right? So no restriction on the x, which means the domain is XCR, right? No limit to it. What do we notice about the y coordinates? The range. Well, for the range, for the y-axis, we do notice that it is restricted. It goes from -1 to +3. So notice that -1 is actually the new minimum value. So before in the original sine function, the minimum value was -1. Oh, sorry, same minimum value. I just realized it's not always going to work that way. But the maximum value is not different. It used to be +1, now it's +3. So we notice that there is a change in the range as well. The amplitude, what about the amplitude? Well, let's go back to our graph here. Well, we can see here that our equation of the axis of the curve, I always like to start with that one. It makes more sense to me. The equation of the axis of the curve is the horizontal line right in the middle, kind of splits it in half there. And we can see here that that would be +1. And the amplitude is simply the difference, the distance from the equation of the axis of the curve to the maximum and the distance from the equation of the axis of the curve to the minimum. And we can see here that that is 2. And we also know that the amplitude is half the distance between the maximum and the minimum. And again, the distance between -3 and +1 is, +3 and -1 is 4, and half of that distance is 2. So the amplitude is very clearly 2. So I didn't show the work for that, but I think most of you know how to find that. We talked about this, the period is 180 degrees, which notice is half of 360 degrees. So pretty interesting, considering that the K value is 2. So again, what we discussed, if the K value is 2, that means you're moving twice as fast. So because this graph is moving twice as fast, that means that you're going to complete the cycle in half the time. So it's going to be 180 degrees as a period. The phase shift. So we haven't talked about phase shift as much, so I'll discuss that really briefly here. The phase shift is basically just looking at how far to the left or to the right you have moved. In terms of how far the start of the graph has moved to the left or to the right. And in this case, we can see here that this cycle, this used to start at 0 degrees, now got moved to 45 degrees. We'll talk a little bit more about the phase shift. It'll make more sense when we get to lesson 5 and especially lesson 6. And the last part, the equation of the axis of the curve, we can see here very clearly it's going to be 1, because that's the horizontal line that goes right in between the graph there. So there is a different way to do this. The other way to apply the transformations is to simply apply the horizontal transformations K and D on the X coordinate, and then apply the vertical transformations A and C to the Y coordinate separately. This is also known as the mapping rule. So this is exactly what we had discussed before, right? So the rule here, this is the mapping rule. It says that you need to take your X coordinate and you simply divide by K, or you multiply by multiply by 1 over K. That's the same idea here. So we take our X coordinate and you divide by K, or you multiply by 1 over K, and then you simply add whatever the D value is. And then for the Y coordinate, you take the Y coordinate multiplied by A, and then you add C. And this is going to be your new X coordinate. So again, this is your new X coordinate here. New X coordinate. And this is our new Y coordinate. Okay. So hopefully that kind of makes sense so far. So again, I'm not going to go over the mapping rule because we've talked about that already. I think most of you are familiar with it. But again, instead of us doing the transforming each of the points step by step, we can actually just apply the mapping rule and get straight to the final answer there. So let's look at an example where we use this shortcut. So for this function f at x, I want you to state the transformations, and then I want you to graph it. And again, just like before, state the domain, range, amplitude, period, equation, axis of the curve, and the phase shift. Okay, let's go step by step here. So our for this graph, for the function 4 cosine of 3x minus 90 degrees minus 2, let's state the a. Well, we can clearly see here that the a coefficient is 4. So that means that we are vertically stretching by a factor of 4. The k value, so the k value here is a little interesting. So you got to be careful with this. Notice that the input in this function has a k value that is not factored out. So we first have to factor it out before anything else. So when you factor it out, you end up with 3 times x minus 30 degrees. And so now we can clearly see here that the k value is 3. And that means that there's a horizontal compression by a factor of 1 over 3. So this always throws people off. A k-value greater than 1, you would think it's horizontally stretched, just like what we did with the vertical stretch and compression, but it's actually horizontally compressed, remember, because if it's a function is moving faster, that means we're reaching it in half the time, reaching each of the y values in half the time. So obviously it's being compressed horizontally. And we say it's horizontally compressed by a factor of the reciprocal of 3, right? So the reciprocal of 3, which is 1 over 3. And again, if this was negative, just remember you would ignore the negative when you talk about the factor, just like we talk about for A. What else do we have? So we have a D value of 30 degrees. And again, we got that by simply factoring out the 3 from the input there. So we have to make sure we factor out the k value first, and then we can specify what the D value is. So if D is equal to 30 degrees, that means there's a horizontal translation of 30 degrees to the right. And the last part, -2, since D is equal to -2, that means that there's a vertical translation 2 units down. So again, don't forget that just like we did before, you always have to factor out the k value. So notice what I did here is I simply factored out the k value of 3 from the input. And this ended up giving me the cosine of 3x minus 30 degrees minus 2, right? Sorry, 4 cosine of 3 times x minus 30 degrees minus 2. So again, you graph this by transforming the key points of the parent function, but notice that the parent function in this case is actually not sine, it's cosine. So look, it's actually the same idea as before. The only difference is that the key points are now different. Is 0 degrees and 1, 9 degrees and 0, 180 degrees and -1, 270 degrees and 0, and 360 degrees and 1. So I'm going to let you actually transform each of these points, but so again, and in class, I would let you transform them. But what we'll do is actually, just to make sure that we kind of know how to do the mapping rule, let's actually go through them step by step. So I'm going to erase this so I have space. So I'll do them up here in the corner here. So I have 0 and 1. What I'm going to do is just apply the transformations and see what I get. So we have, again, let's just do the general rule here. X and Y gets transformed into X over K plus D. And it's going to be AY plus C. So in our case, we're going to, since our K value is 3, that means I'm going to take the X coordinate, which is 0, and I'm going to divide by 3. And then I'm simply going to be adding the D value, which is, again, be careful with this, it's 30 degrees. So I take this 0 plus divided by 30 plus 30. And then for the Y, I'm going to be taking A times Y. So 1, it's going to be, the A value is 4, so it's going to be 4 times 1. 4 times 1, and then I simply add whatever the C value is. In this case, I'm going to be subtracting 2. So I add whatever the C value is, but really because it's negative, I'm going to be subtracting. So this is what I have so far. Okay, so I had a graph calculator, or I can do this all in my head. This is pretty easy. I'm just going to figure out what this is. So 0 divided by 30 is, 0 divided by 3 is 0 plus 30, that's 30 degrees. Sorry about that. And then we have 4 times 1. 4 times 1 is 4, minus 2 is 2. So that means that 0 degrees and 1 got moved to 30 degrees and 2. Okay, I'm going to follow the exact same rules for the next key point. So 90 degrees and 0. I'm going to figure out what the transformation is. So I take 90 degrees divided by 3. So 90 divided by 3. And I add 30. And then I take 4 times 0. And I'm going to subtract off 2. So going through the steps here, 90 degrees divided by 30 is 30 degrees, plus 30 is 60 degrees. So 90 divided by 30 is 30 plus 60, plus 30 is 60 degrees. And then 4 times 0 is 0 minus 2, that's -2. And let's maybe do just one more, because I think you kind of see how to do this. And again, I'll let you just transform these last two here. And I will give you the answer anyway, so you can always spot it. So we have 180 degrees divided by 30 plus 30. And then we have -1, sorry, 4 times -1 minus 2. Okay, let's see what we get. Sorry, there's supposed to be a bracket there. Then we get 180 plus divided by 30 is 30 plus, sorry, 180 divided by 3 is 60. And then we add 30 to it. That gives us 90 degrees. And then we take 4 times -1. 4 times -1 is -4 minus 2 is -6. So now we have 90 degrees and 90 degrees and -6. So I have the first three transformation points. So I'll show you what they look like. So we have 30 and 2 up here, 60 degrees and -2. And of course, this on decimals, it doesn't show degrees symbol there, but you can fill that in yourself. And then we have 90 degrees and -6. And then, of course, if we continue this on, we have 120 degrees and -2 and 150 degrees and +2. So I'll let you finish up these two. I know we didn't show the work for that, but I think you kind of see how you can find out what the transformation is in that case. So this is what the graph looks like. So now if you continue this pattern on, like I said, once you draw one cycle, you simply repeat it and you continue repeating it because you know that the cycles simply repeat over and over again. So if you know how to do one cycle, then you just repeat that over and over again. So we can clearly see here from this graph that the domain is XCR to +2. So notice that the range changes as well. The vertical stretch is going to be 4. And how do we know this? Well, we kind of see here that the distance between the maximum and the minimum, -6 to +2, is going to be 8. So half of that is going to be 4. So we can clearly see here that the vertical stretch also happens to be the same as the amplitude, right? So we clearly see here that it is going to be the exact same. The amplitude is going to be the same as the vertical stretch, the factor of the vertical stretch. So not a coincidence at all. We kind of discussed that we're starting to see the relationship between amplitude and vertical stretch. The highlighted cycle that we had, so the new cycle that we looked at, instead of looking from 0 degrees to 360 degrees, now we're looking at 30 degrees to 150 degrees. So notice that the new cycle that we're looking at, 30 degrees to 150 degrees, means that our period is actually 120 degrees. So you simply just subtract 150 degrees where you end at minus where you started. And that gives us a period of 120 degrees, which is 1/3 of 360 degrees. And of course, our phase shift, where our graph starts. So our cosine graph used to start at 0 degrees, where it was at the maximum point, and then it went down to the minimum point and then went back up to the maximum point. Well, we can see here that now we start our cosine graph at 30 degrees. So the phase shift is 30 degrees to the right. And the last part, the equation of the axis of the curve, we can see here that our middle horizontal line is going to be -2 instead of 0. So the equation of the axis of the curve is actually equal to the vertical translation of -2. So we're starting to see here the relationship between the transformations and the key points of the sinusoidal function. So this is actually the big effect that it has. And again, I would make sure you have this written down in your notes. It's important enough that it comes up in this lesson, it comes up again in the next lesson, right? So make sure you know this. So the amplitude is actually equal to the absolute value of A. Really important that you note that, the absolute value of A. It is not, the reason I put the absolute sign there is because we are going to look at some examples of where the graph can be a reflection of the x-axis for cosine. So for example, if this is the original cosine function, I'll do it in a different color. If in red we have the original cosine function, in green this would be the negative cosine function. So technically the A value would be negative in that one, right? But we'll talk a little bit more about that. But all I need to know for now is that the amplitude is the absolute value of A. So regardless of the sign, you ignore the sign, we're just looking at the absolute value of the A parameter there. The equation of the axis of the curve is going to be C. And so because it's C, then we simply say that the equation of the axis of the curve, because the horizontal line, is simply going to be y is equal to C. The period, we kind of looked at this already, is determined by K, but it's not equal to K. And this is where people make a lot of mistakes. It's not equal to K. What you do is you take 360 degrees and you divide by the absolute value of K, okay? So whatever the K value is, you simply divide it by, so you take 360 degrees and divide by the absolute value of K. The phase shift is pretty simple, and we kind of already looked at that, and we'll talk more about it later on, is simply going to be equal to the D value. And the range, it's affected by the amplitude, the equation of the axis of the curve, and the max and the min, whatever the max and min points are. And to find the max or min points, and this is the last point I kind of want to talk about, a couple of little helpful reminders. So if you want to find out what the maximum point is, you simply take the equation of the axis of the curve and you add the amplitude. And if you want to find the minimum point, you take the equation of the axis of the curve and you subtract the amplitude. So that means that your range is going to go from the minimum value to the maximum value, right? And we didn't talk about this, but the domain for all these functions, for all the sinusoidal functions, is XCR, right? And I think that's pretty clear because we saw that we saw in all those examples that we can sub in any x value into these functions. And two other helpful reminders, although you already have these equations, that's why I wouldn't worry so much about this. The equation of the axis of the curve is simply going to be the maximum plus the minimum divided by 2. The amplitude is going to be the maximum plus the minus the minimum divided by 2. Okay, so you simply take the distance between the max and min and divide by 2. Again, don't make a mistake with the formulas. Sometimes people get focused on the formula, and then this is where they start making mistakes. Always remember what amplitude means, and always remember what the equation of the axis of the curve means. If you know exactly what they mean by definition, then you won't really get them confused. Again, equation of the axis of the curve is simply the point in between the maximum and the minimum. So if you're ever talking about something that's halfway between, you're looking at kind of the midpoint or the average. For average, you add and divide by 2, right? And then for amplitude, because we're finding half the distance between them, well, we know distance means you're finding the difference. We're simply finding the difference between the maximum and the minimum, and then you divide by 2. So notice the difference in the formulas, right? Why they're set up differently. And again, that's the class work. So that's pretty much everything for now. I know that was a long lesson, but I'm hoping that made sense. Again, take the time to go over the note templates so you understand how to do the graphs as well. All right, best of luck.